Hi folks, today we're going to discuss the article entitled Temporal Difference Learning in TD-Gammon by Gerald Tesaro. This is an article written in March of 1995 and has been cited over 2,900 times. To understand this article, it's first necessary to understand the problem space of backgammon. Backgammon is a game that is played with 15 black pieces and 15 white pieces, and it's a game of chance where there are 2 dice. Gameplay is really a gameplay of contrary movement, in which players move their pieces in opposing directions, and the goal or reward of the game is to move the 15 pieces around the board and to be the first to move them from the board. Backgammon has 10 to the 20th possible moves. By contrast, chess has 10 to the 40th possible moves, and there are between 10 to the 78th and 10 to the 82nd atoms in the universe. 10 to the 20th is such a large number that storing and searching for winning moves using existing computer architecture is not an option. Put another way, you cannot take all of the possible moves in backgammon and put them into a table and search. That's just not feasible, again, using current computer architectures. Because of this, you need a probabilistic approach to learn winning moves in backgammon. To understand temporal difference learning in TD-Gammon, it's first necessary to understand that backgammon is a Markov decision process explainable game. A Markov decision process, or MDP, is one where an agent engages in actions and in return receives rewards and state information regarding the environment in which these actions take place. The reward and state information constitute feedback or a feedback loop. Backgammon is an MDP in that players are agents and they engage in the action of moving pieces on a board based upon dice rolls. The reward is the probability of winning based upon board positions or moves, and the state is the current or future position of pieces. Now that we've described what an MDP is, we can talk about the basic idea of temporal difference learning using the following analogy. Suppose you wish to predict the weather for Saturday, and you have some model that predicts Saturday's weather, given the weather of each day in the week. In the standard case, you would wait until Saturday and then adjust your models. However, when it is, for example, Friday, you should have a pretty good idea of what the weather would be on Saturday, and thus be able to change, say, Saturday's model before Saturday arrives. A few key ideas here. First is that you can make a prediction that is taken action about the next day's weather or a state. When the next day arrives, you find the difference between the prediction and the actual weather, a reward. And you do this iteratively for each day, that is each state, rather than waiting till the end of the week. There's a few advantages to this approach. First is that it allows one to change predictions quickly at each state rather than waiting till the end of a particular episode. And you can explore new strategies rather than waiting till the end to explore. Further, you can retain prior learnings and apply to future situations or states. And finally, you can update prior learnings based upon a current situation. Temporal difference learning can also be understood as a backward learning strategy, especially when talking about backgammon. Let me explain. A backward learning strategy can be akin to the notion of hindsight is a 20/20 strategy. In particular, because you cannot use a table to store board positions, you learn past board positions, or states called B, to make predictions about future board positions, such as B, T plus 1. And you maintain a weighted moving average called Z to determine whether past board positions, such as B, T minus 1, need to be updated in terms of relevance. And rewards are understood in terms of an error value. That is the difference between the predicted next board position and the actual next board position reward value. This generally is the TD-Lambda learning algorithm that identifies whether prior understanding of a board positions are eligible for updating. Let me talk a bit more about TD-Lambda. For each action, that is a new board position B, you calculate the following. A Z value that takes a partial derivative with respect to W, or a weight value, and discounts based upon how recent in time the position is. Then you calculate a delta value that finds the difference between the current and future partial derivatives and discounts the future and adds the reward value R. And the W value that updates the weights based upon for each neuron based upon the product of the learning rate, the error, and the weighted average. If the error is large, then lots of updating or feedback is provided. If the error is small, then little or no updating or feedback is provided. Now we're ready to talk about the TD-Gammon model, and in particular TD-Gammon 0.0. The TD-Gammon model is a neural network with between 40 and 80 hidden units, into which were passed 198 board positions. From this, a probability of a winning position was calculated using a value function that took both the state and the weights. And in doing so, would calculate the probability of winning for the next board position. A few key points from this. First, self-play was used to train the model, meaning the same model was used to take an action with respect to white and black pieces. Further, self-play is play that is knowledge-free, meaning no supervised or simulated learning occurred for TD-Gammon 0.0. The TD-Lambda algorithm was used to update, as appropriate, model weights after each new board position or state, so as to constantly improve board positions. And finally, approximately 200,000 games were played to train the model to be competitive with an intermediate level of backgammon player. Outcomes of the self-play approach, new backgammon strategies. TD-Gammon's style of play frequently differs from traditional human strategies. In at least some cases, its approach appears to give better results. This has led to some major revisions in the positional thinking of top human backgammon players. As a result, a few top players began experimenting with the split play, a play uncovered by TD-Gammon. And after some notable tournament successes, it quickly gathered more adherents. Today, the near universal choice is now split play, whereas the slotting play, previously used by human players, has virtually disappeared from tournament competition. TD-Lambda and potential AI ethics and compliance issues. The self-play approach has revealed previously unknown decisions that are not fully understood initially. Further, they're not subject to the benefits or restrictions of convention. Summing it up, backgammon is a Markov decision process explainable game. As applied to backgammon, states are board positions, actions are moving pieces, and rewards are winning the game. TD-Lambda is an eligibility trace algorithm that allows one to update prior learnings of such states, the updates based upon the error rate between the existing and predicted rewards to determine update eligibility. TD-Gammon learned through self-play, and self-play uncovered a number of novel backgammon strategies that changed how backgammon is played. Such novel strategies raise ethical and legal compliance issues and are not easily understood nor always foreseen. I hope you've enjoyed this presentation.